Hello everyone, this is our first lecture on the Fourier analysis techniques. This is basically the chapter number 15 of the edition 10th of Irwin book. So in this chapter we will study Fourier analysis, and that includes the Fourier series and Fourier transform. After going through this chapter, we would be able to determine the trigonometric as well as the exponential Fourier series for periodic signal. So remember that this thing is Fourier series will be dealt for periodic signal. After that, we will understand some waveform and its symmetry, and we will streamline our process for calculating the Fourier series components for such signal. These components will be, of course, mathematical components. Why we use Fourier mathematical components? This is a technique that helps us to convert a visible signal, a signal that you can draw on a paper, to a mathematical equation. So mathematical equations are then ready to use inside computers and for analysis of some sort of equations and something. That's why we use some shortcuts, the waveform symmetry, to calculate these variables a bit faster. We will also find ways to calculate the coefficients of trigonometric Fourier series, and then we will use the same waveform symmetry for reducing our number of steps in calculating them. We would be able to calculate the steady state response of an electric circuit and something related to electric circuits and signals by understanding this Fourier analysis technique. So here we are using the term steady state response. Steady state means that there is no transient in it. So the system is already going stable. It is a through and through system and everything is working fine. So that's why we say periodic voltage. There is no instantaneous voltage. This current and voltage are all periodic. So everything is good and cool. We will also calculate the average power of an electric circuit by excited by some periodic voltage and current. So these are all for Fourier series. These are all for series. And then in the end we would be able to determine the transform pair of signal that are common to our electric systems and use the Fourier transform to calculate the responses of an electric system. So we have a system, let's say this is our system, we have some input and we have some output. So we can study the response of this system in terms of frequency for some defined input. So after that we can have our output, and this whole system and input and output will be in the form of some mathematics. So this is about the transform. So basically we are dividing this whole technique, this Fourier analysis technique, into two parts. The part 1 is the Fourier series and the part 2 is Fourier transform. So today is the first part of this lecture. So we would go to the Fourier series in this. So the contents of our today's lecture are the difference between Fourier series and Fourier transform usage, and this will also include the comparison with Laplace. Okay, I'm clicking this thing so that the writing is okay. So now it is okay. So the comparison would be did. After that, we will know something about this Fourier series. We will explain the connection of Fourier series with the exponential Fourier series, and then we will derive the trigonometric Fourier series from the exponential Fourier series, and after that we will study some symmetries. So symmetries would be the even, odd and half wave symmetry, and based on this we will analyze our signal. We will visually see our signal, and then we will analyze as if it is an even symmetry, odd symmetry, or half wave symmetry, and then we will derive the trigonometric or exponential Fourier series for it. Just for a quick summary, the exponential series has all the terms of the Fourier analysis, Fourier series analysis. So if we calculate the exponential series, then this is a compact form. It will have all the components of Fourier series. But the trigonometric Fourier series, as the name suggests, it will have the cos component and the sine component, and there would be some phase with it. So this theta is equal to j omega, and if we had a t with it, so this will be having. So cos omega t and sine omega t would be the components of the trigonometric Fourier series. Whereas if we combine these both things, e power j omega t is sine omega t plus, with of course a j with it. So this j makes this sine component vertical and cos component horizontal. So this is j sine omega t, this is cos omega t, and this is the combined value. So we call this thing as D, and this thing as A, and this thing as B. We will discuss this thing later. In some documents it is written as C, and some it is written as D. But let's hop in. After that we will discuss this time shifting property. Time shifting property is actually adding another theta with the existing one. So what happens is that we add theta as omega t with some previously signal theta naught. So if we add theta with theta naught, this omega makes this t plus theta naught to add up. Now this is direct addition. In Fourier analysis, since we cannot directly add theta, it must be in the form of some exponent. So e power, let's say theta, and multiply by e power, let's say theta naught. So this will make this thing theta plus theta naught. So basically a multiplication is easily done using Fourier analysis, and that's how we shift the wave. Composite waveform generation will be the composite waveform is that we find the Fourier terms of first wave, and then we find Fourier wave or Fourier component second, and then we can add part by part to get our full wave. So this is what composite waveform generation is done. Frequency spectrum construction, we can easily construct the components of a frequency. Let's say this is our primary or fundamental frequency omega naught, this is 2 omega naught, this is 3 omega naught. So we can discretely draw that what will be the value of frequency in here and in here and in here. So it is just like this frequency spectrum that you see in your music systems, or when you use Photoshop and check the color spectrum. So basically it is just like that thing. Component analysis of the frequency or colors is same thing. So we check if the fundamental frequency is repeated by 2 times when on its second harmonic, or third time on third harmonic, and whether it is attenuating or it is grading up. So we'll check this thing. So let's discuss the usage of Fourier series and the transform. Fourier series is used to represent a periodic signal. Means that if the time period of a signal does not exist, let's say the signal is like this and it is repeated from minus infinity t to plus infinity t. So this thing is termed as the periodic signal because it repeats itself after every t naught. So we can say that f of t is equal to f of t plus t naught. एक टाइम पीरियड के बाद भी ये जो सिग्नल है इसकी वैल्यू वही होगी जो एक टाइम पीरियड से पहले थी. So let's say this is f of t and this whole thing is t naught. So here f of t plus t naught will be same as this f of t. So I hope you have understood this thing. We will remove this. Okay. Now we will convert this periodic signal into a function by summing up the complex components of it. So what are the complex components? The j omega terms are known as the complex component. So we put an n with it and say n is equal to 0, 1, 2, 3, 4. So this makes an nth component of it up to infinity. So that's how we calculate this thing. We will further discuss it, but for now let's just keep this in mind that we will sum up the discrete complex component. The function depends upon the fundamental frequency and its harmonic. So we call this omega as the fundamental frequency and n as the nth harmonic. So this makes it a 0j0, which makes it a 0 frequency or 0 hertz signal, means a DC signal. So the first one is the DC component. This is the first harmonic, omega. Second harmonic, 2 omega, 3 omega, 4 omega, and so on. Fourier transform is then used to represent a general non-periodic function. So first we were talking about periodic. Periodic had some time period. Now we are talking about the non-periodic. So what is non-periodic? A function that does not repeat with a finite time interval. So let's say we are having a function like this. So now this function is started here and it is gone, let's say here. So it won't repeat itself unless we say that this part and this part is also inside the signal, and here is the minus infinity component and here is the plus infinity component. So we assume that this signal repeats, this whole signal repeats, but before infinity and after infinity. So we can write this thing as कि यहाँ पे एक सिग्नल इसी तरह है और यहाँ पे भी एक सिग्नल इसी तरह है. So the time period is infinity. So we say f of t is equal to f of t plus t naught such that t naught is equal to infinity. So this is the first thing that you should keep in mind, that the non-periodic signal is periodic if the time period is infinity. जो नहीं हो सकता वो हो सकता है, लेकिन टाइम क्या होना चाहिए? Infinity. If someone is not coming, so you say he will come, but after infinity time. Okay, so that was a technical joke. The function is continuous with respect to frequency. इसमें जो फंक्शन है इसमें फ्रीक्वेंसी की कोई भी हम कंपोनेंट पुट कर सकते हैं, 0, 0.10, नॉट लाइक दैट फोरियर सीरीज के क्या करें उसमें सिर्फ हम 1 ओमेगा 2 ओमेगा 3 ओमेगा, इसमें कोई भी ओमेगा की वैल्यू कोई भी इंस्टेंट हम इसमें पुट कर सकते हैं. सो दिस इज द सेकेंड डिफरेंस. फर्स्ट डिफरेंस, द टाइम पीरियड इज इन्फिनिटी. सेकेंड डिफरेंस, the function